Hello everyone. In this lecture, we will see the notion of countable sets. We will see the definitions as well as certain important properties of countable set. So let's begin with the lecture by the definition of countable sets. Basically, when we talk about the countability of a set, it means that the number the number of elements in that set can be enumerated. It need not be finite always. Definitely the finite set is also a countable set, but it need not be finite always. Okay, and we know how to show. So basically, the set is has a one-to-one correspondence to the set of a natural number, as we know that the natural number starts from 1 2 3 onwards, and it is the main set which itself is a countable. Okay, so if we talk in terms of function, in terms of cardinality, if we say that the given set has same cardinality as a set of a natural number, in that case we say that it is countably finite. Okay, so for a set to be countable, either it has to be either finite or it has to be countably finite, countably infinite, sorry, not finite. So that's a definition. A set A is said to be countable if either A is finite or there is a bijection f from A to n. Now here the bijection may be from n to A also. If there's a bijection from A to n, definitely there's a bijection from n to A, which is so a set which is countable but not finite is called as countably infinite set. Okay, basically when I set a more general definition of A when it is countable, the number of elements in A or the elements of A can be listed. Say for example A1, A1, A2, A3, and this goes on like the terms in the sequence we can list. Okay, so therefore now since there is a bijection from A to n corresponding to each n, okay, if we are talking about the uh, say reverse, so if there's a bijection from A to n, then definitely there's a bijection from n to A, and so therefore corresponding to each I in n, there's an element in A, okay, which we denoted as g of I, and that element can be listed as ai if we have listed A in this way. Okay, so this is how the enumeration is done. A set which is not countable is said to be an uncountable set, and an obvious examples of a countable set we will come across some more example, but let's see some obvious example of a countable sets: set of natural number itself, set of integers, and set of positive integers. Now here we can produce the bijection from the set, this set to a natural set. So to prove the first one, that n is countable, the bijection that we can have, see, remember that the bijection you can produce from that set to a set of natural number, or you can produce from a set of natural number to that set. Okay, so here the obvious bijection is that each I goes to I. Okay, so this is the bijection one can very easily prove, and the bijection that we can define from set of integers to a set of natural number. I'll just define it, one can very easily prove. Okay, so you should know how to produce a bijection. It is exhibiting a bijection from a set of integers to a set of natural number. What I'll do is that I'll send all the positive, all the non-negative, sorry, all the non-negative integers to one part of a natural number. We call it as the even natural number, and I'll send all the all the negative integers to the other part, that is the odd natural number that we have. And so we define it in this way: g of n goes to 2n plus 1 if n is greater than or equal to 0. So 0 will go map to 1, then 1 will map to 3, okay. 2 will map to, so 2n plus 2, this should be 2 will map 1 will map to 4, 2 will map to 6, and this goes on. And if n is strictly less than 0, then in that case I'll define it as minus 2n minus 1, isn't it? So if you take minus 1, this should map to, say, 1 2 3 4 5. So minus 1 should map to 2. So minus into minus plus 2 minus 1, okay. So we are mapping this minus 1 to 1, not 2, and minus 2 will map to 3, minus 3 will map to 5, and this goes on, okay. So with this, definitely it maps accordingly, and one can very easily show that this is 1 1 as well as on 2. And for the third one, we produce a bijection from Z plus. Z plus is the set containing 0 1 2, and this goes on, right? So the set of non-negative integers to n in this way. Definitely if it contains 1 2, then we can consider the inclusion or the identity map. So we define h of n. So this is just a shifting. You shift 0 to 1, 1 to 2, as the set of natural numbers starts from 1 onward. So you can shift n to n plus 1, okay, for each n in natural number, for each n in Z plus. So this is again 1 1 as well as onto map. So we list down some of the important properties of a countable sets over here, and in fact we look at the slightly stronger version of a countable set. Now in the definition, we want a bijection from a set to the set of a natural number. So the question here we have, just like a finite set, is it enough to have a 1 1 map from the set to set of natural number, or onto map from set of natural number to the set itself to show that it is countable set? So that we will see in some of the properties which we will list down. Property, or the first theorem, equivalent statement, that is just now which one I have said, which is true for a finite set, and so it is also true for a countable set as well. So for a non-empty set, definitely an empty set is also countable, because empty set is finite, so it is a countable. So for a non-empty set A, the following are equivalent. So the first one, this is like a definition of an equivalent set. A is countable if and only if there is a bijection map, there is a 1 1 map from A to natural number, and it is again countable if we can produce an onto map from n onto A, okay. So the idea of the proof is again similar to the analogous result in a finite set, which we have. So first, if we prove that the function is countable, so first we will prove 1 implies 2. Now the problem is only when the set is finite. So in that case, we know that there's a bijection from a set to some subsection of a natural number. Okay, so there's not a bijection from a set to a natural number. If it is countably infinite, then definitely there's a bijection from a to n, and in that case we can say that the map itself is a 1-1 map from a to the set of natural number. To discuss the case when a is finite. So if a is finite, we know that there is a bijection f from a to in, which is a subset of a natural number for some that depends on the cardinality of a for some n in n. Okay, so now how do we produce a 1-1 map? So this, since this is a bijection, this is a 1-1 map as well. Okay, so we just want a 1-1 map from a to a natural number. So how do you produce a 1-1 map from a to a natural number? See, the producing that, it's very simple. You just extend this set in to a set of a natural number, whole natural number. We already have a 1-1 map from, this is say 1 2 till n. We have a 1-1 map like this. Okay, now we want a 1-1 map from a onto a subset of a natural number which is quite bigger than this in. So how do we produce that bijection? I mean, how do we produce that 1-1? So we simply want a 1-1 map. It need not be a bijection. So in that case, see, you can see that through the same map, it's very impossible to produce a bijection from a to n. But in fact, we can produce the injective map, considering the domain, considering the codomain as a set of a natural number and as the same function f. So we define a map G from a to n by, with a similar way. The domain is same, so we can define a mapping. The g of a is same as f of a for each a in a. Now, since now a f from a to in is 1-1 map, definitely g from a to n has to be 1-1. But for sure, this is not an onto map. But we just want an 1-1 map. Okay, so then g is 1-1 as f is. Okay. Now, if it is countably infinite, if a is countably infinite, then we already have a bijection from a to n, and that itself can be considered as a 1-1 map. There exists a bijection f from a to n, okay, which itself is a 1-1 map, hence it is 1-1. So the same map that we can consider, which is a bijection from a to n. Yeah, let's prove the second part, that is 2 implies 3. So in this case, what we need to show is that if there is a 1-1 map from a into n, then we should be able to produce an onto map from n into onto a. Okay, so let's assume that the second statement is true. So let's say that f from a to n is 1-1 map. Okay, so we have a 1-1 map, something like this. This is a, and this, the bigger set, is your n. There's a 1-1 map which is given. So from that 1-1 map, how can I produce onto map? That's a very interesting fact. From not, okay, not you don't want to onto map from A to N. In fact, we want to map from N to A, which is onto. Okay, so that's a very interesting result. So what we will do is that now this F, if I restrict the codomain of F to F of A, then definitely this will be an onto map, right? And since this is an 1-1 map from A to F of A or A to N itself, every element over here will have a distinct image, and so every element in f of a will have exactly one pre-image, and so every element in set of natural number will have at most one pre-image through f. So this element in f of a will definitely have one pre-image. See, we are in the process of producing an onto map from N to A, from here to here. So that we have to produce using this f itself. So there is no problem if the elements belongs to f of a. In that case, we can take the map. We can map this a to f inverse of a. This is an element, right? So if this is an element, say k, then this I will map to f inverse of k, and there will be only such element because this A is 1-1 map. Okay, now what about those elements? Because since we want mapping from N to A, every element of N has to be mapped to some element of A. Okay, and in fact that is going to be an onto map because every element in A will have a pre-image in that case. Obviously, if even if we take an mapping from f of A to A, it's going to be a onto map, but we want a mapping from N to A, so I cannot avoid those elements which is lying still outside this f of A. So what I'll do, I'll fix one element, say C. Okay, then definitely again I'm telling you that in this case that if this n is not same as f of a, if there is at least one element lying outside this f of a, then whatever the map that we will be having from n to a will not be 1-1, but definitely it will be onto. So I'll just fix one element, say C, and all those elements which are lying outside this n, I'll make it map to this C through this new mapping. That's it. So that's a whole idea. So how do we define? So I'll fix a point in A. I define a map G from N to A in this way. The idea, I'll put it in words. So I'll map G of N. I'll map N to F inverse of N if N belongs to F of A. Right? Because F of A is a subset of N in this case. And if it is not, I'll map it to some C which is fixed already in A. By the way, this C is not empty. I mean, A is not empty, so there is at least one such element. So there is an element C in A. Now this is very easy to see, observe that this is an onto map. So in fact, how do you show that it is onto map? You just look at this G of F of A. This is what? This is entire A. G of f of a is entire. In fact, G of n over here is entire A, because G of f of a is equal to A, and all the other element which is lying outside this f of a also map to an element in A, and therefore G of f of a, G of n is same as A, which is so that means the image of the domain is exactly same as the codomain. This implies that G is onto map. Okay. Now, by the way, why this is true? Because by the way, why this G is very well defined? Because F is 1-1. Okay. So you can justify here that since F is 1-1, G is well defined. See, otherwise it would have been not one. I mean, well defined, because see, since A is 1-1, F is 1-1, every element every distinct element in A has a distinct image. So if it has the same uh, mapping, if two elements in A map to the same element, then in that case we could not have defined G in this way. F inverse of n in that case could have more than one element. So in that case, that function is not valid. Okay, so that's it. Now there's one more part that is left, that is 3 implies 1. So what is the tree? We have a 1-1 map from onto map from n to a, and we want to show that a is countable. Let f from n to a be onto. We will. What is happening over here is that you have a natural number, set of natural number, okay, and you have a set a, and this is an onto map. Onto in the sense every element in this set A has a pre-image. Okay, so if I consider f inverse of A, then this will have at least one element in the set. Okay, we cannot say about the maximum, but minimum it will have at least one element. So the question is now how to produce a bijection from the set A to n to show that A is countable. Okay, now the task is very simple. Get a well-defined map from A to n itself, A to n from F itself. We just need to consider the one element of F inverse of A, as the set F inverse of A will contain at least one element. Otherwise what will happen if I just consider a mapping as F inverse of A, then that will not be valid, because you may have two elements of n mapped to the same element, say a, true via f. Okay, so the natural way of producing that mapping from a to n via this f is you just keep on choosing the minimum of f inverse of a. Okay, so that is the whole idea, and if you collect all such if you collect all f inverse of the inverse image of a, it's going to be a subset of a natural number. It will never be empty. It's going to be a subset of a natural number, and since it's a subset of a natural number, we can list them, in one order. That is, we can arrange them in an increasing order using the value ordering properties. Okay, so that is the whole idea, and once you list them, you can again redefine we can again define a mapping from a on to n the way we want, so that we get an 1-1 map from a to a set of a natural number. Now there are two cases that is occurring over here. If a is a finite map, then that sequence of arranging will get exhaust in after certain step, and if it is infinite, then we will have a infinite list of element in the inverse image. Okay, so let's start with the definition, with the proof of this. For our convenience, let's give the notation for f inverse of each element in a. So let me take E alpha as f inverse of A for every A in A. Now this is an non-empty set as f is onto. Okay, so this is in fact a collection of I'll call this as EA. It depends on the number of elements in A. For each A, we define f inverse of A, and it's a set containing at least one element. Okay, so each E alpha, each EA is actually non-empty for each A in A, because since the function is onto, there is at least one element in the inverse set of a inverse image of A. Okay, so F is onto, and since the function is from n to A, inverse image of each element is a subset of n. Okay, so also note that. Sorry, subset of n. Therefore, by well ordering principle, the element of EA can be arranged, can be least, and so we can find the least element in this EA. Okay, so by well ordering property, there is a least element in there is a least element of EA. Okay, so now for each EA there is going to be a least element, so I'll consider in general it as NA. So let NA, so NA be the least element of each EA. Okay, so this depends on the number of element in A. And so if we collect this least element, the set of all the least element of EA, then that is either finite or it's going to be infinite. That actually depends on the number of element in A we have, because for each A in A we are considering the set of an A. So then is either finite or infinite. So if it is finite, I mean, in which case this can be finite if the set A itself is a finite. Okay, and in which case it is infinite in the case when A is countably infinite. Okay, so basically we are proving that 3 implies 1, so we are proving that A is countable. So if it is finite, so there are two cases, and the second I'll discuss only one case, the second case can be discussed in a similar way. Only thing, if it is infinite, then that process is never ending process. Okay, that is arranging the element of E alpha. Okay, or arranging the element of this set NA. So if this set NA for each A in A is finite, this is basically what does this NA stands for? NA is nothing but the minimum of F inverse of A, nothing else. Okay, so as simple as that. So we are just putting it in the notation form. We have already dealt with this kind of definition of a function, construction of a function. So if this is finite, arrange them as a finite sequence. Now that sequence will be finite. Arrange them n1 less than n2 less than n. This goes on. Say finite, that means there will be a bijection to some subsection of natural number n. So as a finite sequence. Uh, so it becomes countable. Okay, now so to show that it is finite, how do we produce a bijection from set A it has to be some subsection of ik, some section of a natural number, some subsection of a natural number, and the number of subsection denotes the number of element in A. And so we know that for each A in A we have this n1, n2, nk. So that actually says that the number of elements in A is nothing but k. So we need to produce a mapping from A to that subsection is nothing but ik, which is this set. It contain all element starting, okay, all natural numbers such that n is less than or equal to k. Okay, so this is I define by, in a very simple way, you define it by j of a is equal to j if, see, there is a mapping from set of natural number to a. Okay, so what will happen is that, sorry, there is a mapping from where to where, which is the onto mapping that we have. There is a mapping from a to n. Okay, and the number of elements which we have chosen in this case from A is n1, n2 till nk. So these are the element from where the mapping from n to A, right? So which is onto. So for each A we have produced NA. So NA is nothing but the natural number again. So how do I map this A to J when this NJ over here is mapped to this A in A. So if f of nj is equal to A, okay, and this is true for each j till k. So this is how J is defined, and in fact to the observation you can see that this mapping is 1 1 as well as it is onto. So how do we show that this is 1 1? So first, to show G is 1 1 or injective, so we need to start with two element in A. So let A comma B be in A. Okay, so if A and B are in A, then definitely there will be some element in N such that its image is equal to A and B respectively, as F is a mapping. Okay, so therefore there exists N I. Okay, by the way, why this is true, as F is an onto map. Okay, so since F is an onto map and A and B are the point coming from A, there will be some element, these two elements will definitely have say some free image because F is an onto map. So there will exist Ni and Nj in N such that f of Ni is equal to A and f of Nj is equal to B. Okay, as F is onto. Okay, now let me say that this A is not same as B, then I have to show that G of A is not same as G of B. So if A is not same as B, then definitely from here f of Ni will not be same as f of Nj, right? So if f of Ni is not same as f of Nj, then this I will be different from J. That is the only possibility that we can have. If I is different from J, then this G of A will be different from G of B, because the way G is defined, whenever f of Nj is equal to A, G of A is equal to, it takes a suffix J. Okay, so that's it. So therefore we see that the function G is 1 1 over here. Secondly, to show that G is onto, let me take any element in ik. So the element in ik will be from 1 to k. So let me take j from ik, which will be either 1 2 till k, right? So let f of j let f of nj be equal to A, which belongs to A. So definitely, since uh, f is a mapping from n to A, for each natural number there will be a image, and so for nj also there is going to be an image. I'll call it as A, okay, which belongs to A. Okay, so this would implies that f of nj is equal to A. This would implies that g of A is equal to G by the definition of G. That's it. So from here you see that G is 2. So this proves that G is bijection, and therefore A is finite set containing k element. So in the later case wherein you are saying that this set of NA is infinite, in that case you will prove that A is a countable set. In fact, in that case you just have to show that there is a bijection from A to natural number. So that I'll leave it as an exercise. If is infinite, then we can show that A is countably infinite. That is, it is not finite, but it is countably infinite. So you need to actually produce the bijection from A to n in a similar way, exactly in a similar way, because see, this is infinite means for each A in A. So you can enumerate the number of elements in the set of a natural number. Okay, so you show that it is countably infinite by listing the elements in NA in this way, and this goes on. Since it can be listed, we say that this set is actually countable set. Okay, because for each natural number you can see that there is an n. For each I in n there is an ni. Okay, so you define the mapping in a similar way and show that it is 1 1 and on to from the set A to n, and which says that the set A is countably infinite, and therefore the set A is countable. Okay. So let's get into the next property. Suppose we have a 1 1 map from A to B. This is again similar to a finite, the property of a finite set. What does it says that if you have a 1 1 map from A to B, and if B is countable, then you can say that A is also countable. Okay. Then A is countable. And in a similar way, if you have a, so that's the first one. The second one, if you have onto map from where to where, from A to B is onto, okay, and if A is countable, then B is countable. You can just recollect the property which we have proved in a finite set, a similar property which we have proved in a finite set. And the third one, a subset of a countable set is also countable. Okay. So see, in fact, these results are very easy to show. We can use the previous property. As we have seen in the previous property, to show that a set is countable, it is enough to produce a 1 1 map from that set to a natural set of a natural number, or it is enough to produce an onto map from a set of a natural number to that particular set. Okay, so now here we use the same idea. What is given, let me try to prove this in a very simple manner. What is given is that A to B is 1 1. Okay, and you are given that B is countable. Okay, B is countable. So since B is countable, see, in fact, you have a stronger definition, that is there is a bijection map from B to N, but you can use a weaker one, that is you can say that there is a, by the previous property, there is a 1 1 map G from B to N. The reason is very simple. See, if you have a 2 1 1 map and you want to show that this A is a countable, and if you can composite this map and find a map from A to N by this composition, then it's again going to be a 1 1 map from A to N. So if it is 1 1 map from the set of from set A to the set of natural number, then again by the previous property you can say that set A is countable. Okay, so that's very simple. So combining these two, so therefore G composite F. See, F is, first of all you need to see whether we can define G composite F. So let's see the domain of G. The domain of G is B, which is the codomain of B. So definitely F of A will contain in this B. So we can define a mapping from we can define G composite F. In fact, G composite F, because F is a map from A to B. Okay, so F is a map from A to B, and G is a map from B to N. So if we have something like this is F, this is G, and this would be map from A to N, G composite F. So G composite F is a mapping from A to N. This is a composition of 2 1 1 map, is also 1 1. So we have produced a 1 1 map from set A to a set of natural number. This says that A is countable by the previous property. And similar way, in fact, you can show even that if A to B is on to and A is countable, then B is countable. So I leave this up to you. In fact, you can use the fact that if A is countable, then there is a onto map from N to A. So you have a mapping from N to A and you have a mapping from A to B, which both are onto N. Therefore, the composition from where to where? From N to A and A to B. So N to B. Okay, basically this will be a composition from N to B, that is F composite G will also be on to map, and therefore it is countable. So the first one we have done, second one I leave it for the exercise, as it is very easy to prove. The third one, what? A subset of a countable set is a countable. So let me take A to be a subset of B and B is countable. Okay, but what I need to show is that A is countable. Now see, since B is a countable, there's a mapping, there's a mapping from B to set of a natural number. Okay, in fact we can use even the above property. We can define a mapping from A to B, which is 1 1. And what's a trivial, because you know that A is a bigger A is a smaller than B, we can define a mapping called as an inclusion mapping. So we define a mapping from A to B by f of x is equal to x for each x in A. This is very well defined. If A is a proper subset of B, then this is not a onto map. Okay, if A is equal to B, then this is surely going to be onto map. But this is definitely, no matter what is A and B, I mean whether A is a proper subset of B or not, this is going to be a 1 1 map, and therefore I can use the first property itself. If A and B is 1 1, and if from A to B, if f from A to B is 1 1, and if B is countable, then A is countable. So here we have B is countable, and therefore this should imply A is countable. Okay, then f is 1 1, and since B is countable by 1, A is also countable. So that's prove the third one. There are some trivial results of countable sets, which are easy to observe, and I'll state it. In fact, the proof, you can just look for the textbook to find a proof for this. Okay, so if R is countable set, and AI is a countable set, is also a countable set. Okay, basically I is taken for as an intact set over here. So what basically this says, this result says that the countable union of a countable set is countable. Okay, AI is countable for each I in I. Okay, then this set is countable. So this says that the countable union of a countable set is countable. That's the first one. Not only that, in fact, uh, cross product of a count, that is a Cartesian product of countable set, is also countable. And in fact, a finite, not only Cartesian product of two countable set, a finite Cartesian product of countable set is countable. Okay, here I want you to find a proof for this two statement. These are the trivial, these are one of the standard properties of a countable set, and in fact you can get the idea of producing a bijection or even a surjective or even an injective map as per the requirement. You can use the property which we have proved just now, the equivalent statement, in fact this one, to get, if not the bijective map, you can get a mapping from the union of set AI to a natural number which is 1 1, or you can get an surjective map from a set of natural number onto this union of each AI. Okay, some exercises from the textbook. Okay, yeah, thank you for watching this and have a nice day ahead.